Okay, welcome to the second stream in the series. I did do something off stream, which is that I remembered that Odin format exists. So I've quickly added this Odin format into the project we've started. It's not super interesting. It just means that when I auto format the code, it will. The most important thing is it will use spaces instead of tabs, because I do like having the I can't do it because Neovim replaces tabs with spaces. I do like having it show tabs when they do come up, just so I know if I'm using them consistently or if I'm using spaces consistently. But I do find it distracting to have them all showing, whereas if it converts to spaces, then it looks neater. So we're going with that. If I do a quick git log, I think all I did was, I ran out Odin format, and that is the only change since the last little bit of coding we did. So where we're up to now, if I just go and run the program, is we can open this little window. We've kept it a fixed size, but it's a sensible window. We can close it. I think we now start having to think about how we actually set up our Vulkan pipeline. I was umming and ahhing about this a little bit, because one option would be to just copy everything from that Bracky platformer project, or I've got a couple of other little projects that were similar. I'm not sure that that's all that sensible, mostly because I assume this isn't just me. If I have working code in front of me, I feel like my brain turns off, and that probably isn't a good way to learn anything. It's probably not interesting to watch either. So if we were going to do that, we might as well just copy paste the projects across. I was also thinking that I could go back to using the Vulkan tutorial. So if you're also a slightly curious person like me who's just looking for a way to get started, this is the place that I started learning how to do these various little odds and ends. But I'm also not sure that's the best place to start. Again, they are very opinionated about how you do things. They're providing you, at the end of the day, a working example. They do so with a bunch of nice explanations, which is obviously good. But they're also setting you up for 3D rendering. Like if you were to jump ahead, I guess to loading models maybe, somewhere at the bottom here, yeah, it's showing rendering 3D scenes at the end of it all, which is obviously useful and interesting information, but it does mean that things aren't set up exactly the same way as what we're aiming for. Notably, what they're doing is more complicated than what we're aiming for. We're deliberately doing something pretty simple. That said, a lot of the setup and presentation stuff is probably actually really similar, right? Like all of these steps are steps we're going to go through. So we'll take that as a backup. But I was kind of thinking that what we could do is, I've downloaded the Vulkan spec. I've never tried using the Vulkan spec directly and trying to sort of pull the idea out of my head and then go to the Vulkan spec and work out what to do from there. So this may be a disaster. I have found in the past when looking things up that the Vulkan spec is kind of absurdly wordy. Sorry. Which is fair enough. It's not intended to be read like a book. It's a reference document. But I don't know. Maybe we learn something this way, right? Obviously, the Vulkan tutorial is an opinionated document that is telling you a way to do things. It might be that we learn something out of this. I did grab the version 1.4 of the Vulkan spec. We've currently only enabled the API version 1.3, so there will be stuff in here that we can't use, but I think it always flags places quite clearly. For example, like here, this is provided by VK1. So if we do see something we're interested in that's on a higher Vulkan version, we can work that out. But yeah, I think let's start here if this is a nightmare, we'll jump back to the Vulkan tutorial, and if we just struggle to make any progress at all, maybe we do resort to a bit of copying out of the Brachy's platformer stuff. But all that is to say, we need to work out what we do first. So we've kind of done this initialization step. I did note, listening back to the first stream, my explanation for this sucked. I make no bones, I don't understand this chunk of the spec very well. It's the kind of thing you do once right at the start of a project and then never have to touch again. So I'm not even sure I'm going to take the time now to get my head around it better. I think it's one of those that you come back to when things are proving to be like really difficult. I think there's kind of two sensible places we could start. One would be setting up the validation layers, and one would be setting up our physical device and our logical devices. So I think maybe we start with the devices and grabbing the device queues, and if we just hit a dead end and things aren't working, maybe we'll go back and we'll add the validation layers as like a useful step towards sorting that out. If we don't hit any major issues, instead of that, what we'll do is we will go back and add the validation layers later. Because even if we don't hit issues here, we will hit issues eventually when it comes to like synchronizing things and managing our allocated memory. There's just too many places to mess up. So that's definitely worth the effort at some point. So, my God, is it worth reading all of this stuff? We would like to create a physical device. One of the things, and again, this is another one of those common Vulkan API patterns that we're going to see a whole bunch of times, is these enumerate calls. They're slightly confusing. So the way they work is, so in this case, enumerate physical devices is going to send a query to, I assume to the operating system, to say what physical devices are that have like graphics drivers that I could plausibly use to either do computations or to do graphics work and present to a screen. But because it's all C and you don't have kind of like easy garbage collected memory management, you actually end up having to do this in two calls. So you notice that it'll take a device count as a pointer to a number, and it'll also take a list of devices as a pointer to physical devices. The reason it does that is you have to call it once with null passed in. Is that true? Yeah, you pass it in null for physical device, and that's a trigger it uses internally to say, I'm going to use, I'm going to return essentially the number of physical devices that this machine has available to it in the physical device count variable that you passed in, and then you call it again with a non-null value here, and it will then put the result, which is a pointer to your list of devices, into there. And because we know the length of it, we can now access it sensibly. It is awkward, but it is what it is. We're probably going to end up calling a bunch of these enumerate device or enumerate style calls, so we might end up writing a wrapper around them. But I think at first we just do the ugly thing. I am wondering if we might want to put this in a split view. I'm just going to wait and see what that looks like on the stream. Yeah, I think we're going to do it. So let's put that over here. And can I collapse this? Is that still reasonably readable? I think that looks okay. And I guess there's nobody in the chat to actually say if it looks okay. So if that's not readable, I'm very sorry. I think my code is readable if nothing else. Do we want to have a think about how we organize this at all? So again, just to recap from the last time, I'm keeping this global context object. It's nasty. It's the sort of thing we're probably going to have to refactor later. But for now, things that we're going to want to have access to in a bunch of places, we're just going to bung in there just to make life easy. We're also going to keep everything in the one package. Again, just to keep things easy. But we can split that package across multiple files because Odin does packaging by directory rather than by file. So I'm wondering if the thing to do here would be to split out a renderer file. And then we can keep the renderer specific state sort of bundled in that one spot. Give it an init function. I mean, if you do go and look at the Brachy platform and stuff, this will all sound very familiar because I think this is what I did in there too. Yeah, let's start doing that. So let's make a renderer.odin .don. We'll come in here. We're still in package main. So what are we going to end up with in here? I guess we're going to end up with a renderer struct. And I'll make an init renderer. Which will be a procedure. Shall we just have it return a renderer? Or do we want to, like, in out a renderer? We could even make a global renderer. I think we'll go ahead and do a renderer like this. Okay. So I guess inside of init renderer, why have you got a error because of the missing return statement? So one thing we could do, which is probably good practice, but not something I'm intending to do everywhere. So a pattern you'll see quite a lot would be something like, you know, if we had the renderer and an OK bool like this, then you can, you know, return something like this to indicate an error state, right? This is one of those places where the multiple return value is nice. And unlike, I guess, like C or something, this is kind of quite ergonomic. It's deliberately designed to be easy to work with. So when you put named variables in here, that declares the variable, so you can then just use them. So if this were to have a field x, it's an int in it, then down here I can just do rx is some number, and that should compile and work. Whereas if I were to instead say that it's just going to return a tuple, then r becomes undefined, and you would have to put something in up here to declare it. That's a really neat pattern. It's a nice way to make sure you handle all your errors. I also think it's going to add a bunch of thinking overhead at this early stage that we don't really want to worry about. So I think instead I'm going to have it just return a renderer. And we're going to take the same approach that we took throughout the window initialization, which is if it breaks, we just panic. All right. So what we want to do in here then is we would like to pick a physical device. So Vulkan is super general, and you can kind of make it do anything that like your computer can do. That's the intention. So we could do things where we check to see if you have multiple GPUs attached, which if you have a integrated and a discrete GPU is not an unusual thing to do. And then we might want to do different types of work on different devices, or things like that, but that's all well beyond our scope in this. So what we're going to do is we're going to keep it super simple, and we're going to enumerate physical devices, and then I think what we'll do is just pick the discrete GPU if one exists, else pick the integrated GPU. I honestly can't remember how to do any of that, so maybe this will be an interesting test of how clear the Vulkan docks are. So yeah, let's see how we go. But so step one will be that we need to call this enumerate physical devices to work out the number of devices that are available to us. So let's come in here. We are going to need to import the Vulkan package, which again, super easy to work with in Odin because it's all vendored in. Count is going to be a U32, and we're going to call enumerate physical devices, and we're going to need our instance, which we can just come in here and grab. So this is the reason to make these things global. We're going to pass in our reference to count and nil. So once we've done that, what we should see is that count should have some non-zero value. So let's go ahead and import format. I guess let's just check that's true. So if we come in here, format, print line, count. Can I just return something to make that not complain? No, I can't. Missing a return statement at the end. Oh, I'm an idiot. Okay, there we go. And I don't know why I've got that renderer like that. Oh, maybe this is another thing that's useful to know. I think in Odin, if I remember right, you can always use kind of this empty object looking thing to mean the nil value of something. So if this were a pointer, this would be equal to nil. Because it's a struct, I think what it ends up being is a zero initialized struct. So if I had something like this, for example, then Odin initializes all memory. So it's not like C where you can sort of initialize a value and it'll just be garbage values will fill, or sorry, you can declare a struct variable and then all of the field values will just be nonsense. Odin by default zero initializes all of the values, so this will be 0 and this will be false. So I think if you do return empty, it will just fill these in as if they're 0. Probably not a good idea to do in general, but a nice way to like quickly just satisfy the types. So yeah, let's go back to main.odin and call our init renderer. In fact, let's just go ahead and call it so init renderer in there. We run this and we get 2. Now the laptop I'm running on doesn't have a discrete graphics card, so one of those devices will be the integrated graphics card that we're actually going to end up targeting. I think one will also be a like a software CPU side sort of Vulkan driver. So I think it's pretty common for things to have the ability to run Vulkan code on the CPU, and it's not a thing you'd want to do particularly, but I think that's why there's a second one. I guess if that's not true, sorry, but I did say in the first stream I'm no expert, so believe me at your peril. So like I say, we've then got our count. We can now allocate out enough memory to hold our physical devices. Embarrassingly, I'm forgetting how to allocate out memory in Vulkan. I think it might be make. So if I call make to built-in proc make, that's not very helpful, is it? Let's jump back to the Odin language reference. I think you use make for strings, and maybe it's like create and destroy for making single things. Doesn't say anything about it there. There we go. So this is doing make for a dynamic string, but we don't want a dynamic string. We're going to just make a simple slice. I keep saying string. Odin has dynamic slices that will have an allocator associated with them, so you can append to them and they'll just grow. But because we're being given the size of the thing that we're going to get ahead of time, we're going to just go ahead and make this a normal slice that's a fixed size. And then a slice is, I feel like I've just called them like either wide pointers or fat pointers in other places. It's just a pointer to some area of memory plus the size of the memory view that we're using. So if we come back here, we should be able to go make a slice of VK physical device count. And that's upset because Vulkan has some nice type stuff on it to say this is like an undiscardable value. We're going to call that our physical devices. Do we want to put that onto our renderer immediately? Maybe? I think more likely than that we're going to want to keep our... I'm not sure. Let's wait and see. So we grab our physical devices. If we're not going to put it onto the renderer, I think we would like to do a defer. I've got destroy in my head as the... This is like the malloc free equivalence. I've got that in my head. Not true though. Should we see? Destroy. Destroy window. No. Let's have a look then. Odin. Memory locations. Can we find stuff that is just the web? Mem doesn't necessarily sound like what we want. Memory deallocation. Does this random person have our answer? Delete. That'll be it. There we go. Thank you, random Redditor. So, does that make sense? We grab our physical devices, then we'll come back in here, we call our enumerate physical devices again. We do the same thing in here. We pass count by reference again because it's the same signature, but this time it won't get updated. And we'll pass. Again, I think what we have to do is a raw data for physical devices, like so. And again, I think I mentioned this in the first stream, raw data will just strip the length off of our slice, so we're going to pass just the pointer through, which works on the API side of this because it has the count already, so that information is already available to it. If we do that, we have a quick look at the docs. So you see in here that this will return us a VK result. So actually, probably what we should be doing is after each of these, maybe what I'll do is something like this. Then this will have a res equals that if res not equal to success, then we do something, and if down here we'll do the same, so we'll say here res is equal to that, and if res is not equal to success, then we do something. So you can get away without doing this, but a lot of the stuff in the API will return a result to tell you if it's going to fail for any reason, and it's generally a good idea to put something in if you're doing something more complete, obviously like add proper handling. I've found it's useful to just put like a little descriptive like panic string, so when inevitably you mess something up, you get something slightly descriptive, just to save you having to get your head back into what that block of code's doing. So let's just say enumerate physical devices failed, and down here in enumerate physical devices, second call. So that should then give us a list of physical devices. If we come in here and we format print line our physical devices, or we've got them, it gives us a pair of pointers. I should have seen that coming. Okay, instead of that, let's do 4 pointer to device in physical devices, format print line, pointer to device dereferenced. Will that do what I want? No, because it's of type physical device. Is physical devices a pointer to an integer related to the number of physical devices available, or an array of handles? Yeah, okay, so they're not structs, they're handles, so there isn't any actually useful information on them yet, I think, is what that's saying. What is the rest of this? This is it just explaining if you pass it in null, then it will return you out that value. So we've explained that already. Gives us these things back. Then to query general properties of physical devices, once enumerated, you call this for each physical device, and it will give you back a list of properties, where properties are pointer to physical device property structure in which the properties are returned, where physical device properties, API version, driver version, vendor ID, device type is probably actually interesting to us. Pipeline cache limits and sparse properties. So we're not going to need quite a lot of this. I'm assuming we're going to need to use API version to check that it supports the Vulkan API version we're using. We're not going to be digging deep enough to worry about the limits. We're just going to assume everything we do is within the limits because we're making such a small and simple game. VK physical device sparse properties. Again, I don't think we're doing anything intense enough to have to care about things being sparse. We're just going to try and keep things dense and simple. So we are now at the point where we've got our handles, and maybe I do want to be writing this all onto the renderer. Okay, so I'm imagining that this is going to end up wanting a physical device on it. Oh my god, if only I could type physical device. And what we would like for this thing to do is to stick it on our renderer. So actually maybe it is useful to use that, so that thing we were saying at the start. So we'll make it into a named variable, and down here we'll return it. Why is that not happy now? Syntax error expected. Have I deleted one too many? Something like that. There we go. You can actually, if you're using named return values, you can just do return. But this is likely going to end up quite a big function. So let's keep it explicit just so I don't confuse myself later. So we've got pick a physical device, gets us to there. I guess what we want to do now is we'd like to iterate over the physical device handles. And get their physical device properties. So for device, yeah, let's do the same thing we just had. So in physical devices, we are going to call this VK get physical device properties. This one returns void, so it can't fail. It will take in a physical device, and it has a pointer to properties, which is the struct it wants to return to. So let's make a properties there, and we would like a properties variable, which is of type physical device properties, and this needs to be a pointer to it. Still not happy. Get physical, because I've typed it wrong. There we go. So that should populate this, and I would like at that point to do a format print line for those properties. We run this, and we see a whole buttload of stuff comes out, which is good. We expect that. One of the properties that we expect to find would be device type. So let's go ahead and see. If we do this, what do we find? Integrated GPU and CPU. Yes, that's what I was saying earlier. So if you've got a integrated GPU, we're going to use your integrated GPU. If you have a discrete GPU, we're going to use that instead. How do we do that? We could do it with the switch, but there's so few cases that we care about. I think I'm just going to do an if, because I don't know if there are other things on there. API version actually maybe is worth. Is there anything in version numbers about comparing? So you have a version variant, version major. So we could check that. I'm going to not bother. I'm going to just assume it works, and I guess it'll just blow up in a horrible way if if it doesn't. But we're going to just say in here, for device in this, do this. If what did I say? Renderer dot physical device is equal to nil, and device dot, what was it, device type? It wasn't. It was. Is equal to. It's not doing a very good job picking up. Physical device has no field device type because it shouldn't be a physical device. It's because I'm looking at the properties. There we go. It's not integrated, it's integrated GPU. My goodness. So if we've not selected physical device yet and we see an integrated GPU, we are going to grab that. Else if properties device type is equal to a device type is equal to a discrete GPU, then renderer physical device is equal to device. And in fact, we can actually do that more neatly, can't we? So we can say in here, if properties dot device type is equal to discrete GPU or renderer, all this up to the end of there. That does the same thing, doesn't it? We'll delete this. So we're going to iterate over each device. We're going to check its properties, and if the properties tell us it's a discrete GPU, we're going to take that one. Else, if we've not found a physical device yet, and the device type is an integrated GPU, we'll take that one. We get to the end of that, and if we format print line out our physical device, it should tell us that we have an integrated GPU. I forgot that it is the handle. If we scroll up, oh, you get a different handle. Cool. Let's show how little I know about that. Okay, I'm going to assume it worked. It wasn't 0, so we have picked something. So I'm going to call that good. At that point, we've got a physical device selected. I think we're going to now have to create a logical device. If we just scroll down a whole bunch. My goodness, what's this? You have a physical device properties 2. This is another one of those things. So I have found reading the Vulkan docs before, you're going to see a whole lot of this where there will be function call 1 and then a function call 2. where function call 2 is basically it's covering for a thing that they missed in the first version of the Vulkan API, where it's often really useful for these things to be extendable. So I think if we look at this one here, physical device properties 2 will look the same as physical device properties 1, except it'll also add this pnext. So you can chain together multiple extensions. I don't know that I've had to use it very often, because what I'm doing is generally really simple, but good to know about. And again, it's just another one of those things that will make everything in the docs a little bit hard to get through, or in the reference manual even. So we scroll past absolutely everything. In fact, is it better to jump? So once we've made our selected our physical device, we now want to make a logical device, which is how are we going to actually interact with the physical device for the purposes of the API calls. I'm not sure I fully understood how queues work and queue families work the first time that I went through all of this, so maybe this is worth looking at a little bit more carefully. So device objects represent logical connections to physical devices. Each device exposes a number of queue families, each one having one or more queues. All queues in a queue family support the same operations. All queues in a queue family support the same operations. Okay, so I think the vague picture I have in my head is that queue families are sort of destinations on the GPU that we can submit work to, and depending on, I guess, the architecture of the GPU, not all queue families can support all operations. But by the way that they're designed, they group a bunch of queues together, which are all capable of, I guess, having work dispatched to them. And all the ones that are grouped into a queue family are capable of doing the same work. So you can sensibly say, okay, GPU, I need you to do some graphics and presentation work. And if the queue family supports it, all of the queues in that family will be able to do that work. We've missed this. Okay, so querying the physical devices for their queue family properties is described in the physical device enumeration section. I thought that came on the logical device step. Interesting. So we may have to jump back to that. So what is this saying? A single logical device can be created from multiple physical devices, so we're not going to be doing that if those physical devices belong to the same device group. Okay, so that's a feature I don't think we're going to end up using. Enumerate physical device groups. So yeah, we're not using that. Can we jump back into here? So I thought we were skimming along into the logical device creation stuff in order to find all the queue stuff. But apparently it's all in here. And it's not broken down any further in the sidebar. So we need to skim more carefully. So we have the physical device properties, which is what we've done in there. The physical device properties. What are the queue properties on the physical device properties then? Vulkan 11 properties, has a whole bunch of stuff on it. I guess it's 1.1 and 1.2. So it's going to be a 1.3. And the 1.4 properties. VK physical device ID properties. What are you? Defined as this or the equivalent. Device UID. Yeah, I don't think that's us either. Physical device driver properties, I don't think it's us either. Okay, I'm starting to doubt this plan of just working through stuff from the spec, because there is a lot in here that I don't think we're going to need. And it's making it a little bit hard to actually find the stuff we do care about. So yeah, we're now getting into all the different extensions. maybe the move is to go and download a copy of the docs without the extensions, because I think that that does exist. Or maybe with just the KHR extensions. There we go. Okay. So the VKQ family properties struct is what we want. Okay. I think, is there a way for us to stick a little thingy so we can find this more easily next time? We have bookmarks, we have annotations, and we have thumbnails. Can I stick a bookmark in here? Nice. And what we're saying in here, this is Q family properties. Cool, because that was a trial to find. Okay, picking up where we were. To query the properties of queues available on a physical device, you call VK get physical device Q family properties for a physical device. Again, it's another enumerate call. Is it another enumerate call? Yeah, the count and properties, but it's not called enumerate. It's a void function pointed to an integer related to the number of Q families available or queried, either null or pointed to an array if it's null. Yeah, okay, so it does work like an enumeration. So we've picked a device, and then given that device, we're going to call VK get physical device Q family properties. You can see from that completion there, again, this is another one of those places that there's a bunch of different versions of this, but we're just going to stick with the bare bones one, and it is going to require us to grab our renderer. I might rename renderer to R, just going to be typing it out a lot. Is that super lazy? Okay, we're going to leave it as renderer, because I'm pretty sure... Okay, sorry, let's just get through it. So we're going to pick out our physical device. We're going to have a count, which we're going to have to give a reference to. Oh, it's got a thing missing, and a nil in there. I wonder if it's a get instead of enumerate, because it can't fail. I wonder if that's a semantic difference they make. God knows. So we're in there. And count has already been defined. So maybe the move is to pull this out. So I think I mentioned this briefly in the last video. One thing I have found is when writing code that I really don't understand very well, and specifically writing code for myself in a project nobody else is going to be collaborating on, I found that I prefer wrapping, I guess, like quote unquote functions into scope blocks rather than actually pulling out functions. Mostly because I end up having to scroll up and down and reread it all a bunch. So one of the advantages of doing that is it keeps all my little local variables actually local, so I can use really quick names like res and count for my results and counts without hitting naming conflicts or without accidentally reusing a variable from earlier. I'm not super settled on the idea, but I have found it works reasonably so far, so we're going to go with it for now. The other thing that is nice is if I am later working on this, so obviously the one thing this doesn't offer you is code reuse. You couldn't, if I needed to now pick a physical device from somewhere else, I couldn't use this, but this is already basically a function, right? So if I come into here and I did like foo is a proc that does things, I can then just rip that out and put it somewhere, then that just works. So it's easy enough to refactor out. So if you're looking at this thinking that's abysmal, that's my thinking. I'm not telling you it's right, but it's what I'm going with for the time being. One thing that I think this lends itself to that is that there's a whole bunch of stuff we're going to do once setting up a renderer. So it doesn't matter if things aren't reusable, because we're not going to reuse them anywhere. So what are we doing here? We're going to pick our device Q. And I'm going to make that singular, because if I remember right, there's a whole bunch of different types of Q. So you have, can I remember? graphics queues that are capable of doing graphics pipeline work, presentation queues, which can handle presenting to the screen, transfer queues for moving things in memory. For example, you might need to move something from the host device memory into the GPU host visible memory, and then from there into high performance like device local memory. You know, if you were doing like a 3D renderer using a very complex mesh, that can be worth doing. And if you're doing this very, very efficiently, you might want to have a separate transfer queue to do that, so you're not using up resources from your queue that you're sending work to, or your queue family that you're sending work to, for transferring memory around when you want it to be doing graphics work. I think we're going to get away with a single queue family. So all the work we're going to be doing will be presentation and graphics work. And if I remember right, I think the spec specifies that any queue that can do graphics work can do presentation work. That might not be true. I think that's true. So I think we can just grab the one queue to keep life simple. And if we need more later, we'll extend later. But I mean, I can come up here. I'm going to make myself a queue. I'm hoping it's literally called queue. It looks like it is. It's a handle. Sweet. So we're going to have a queue that we can submit work to later. And in here, we're going to want to be able to pick out a queue. So like before, we're going to need a count, which is going to be a U32. And again, because it's Odin, it's zero initialized, so it does the same thing as if we did this. We're going to get our queue family properties, which will enumerate it so that we can then come in here and we can go make... what actually is this then? So let's go ahead and say queue family properties. I'm slightly confused as to what it's actually giving me. The queue family property count. An array of properties structures. So I guess, is this really queue family's properties? It's where it's annoying having plurals on things. See, it's not the number of properties on a queue family, it's the number of queue family properties structs that will go into this array. So I'm going to go with that slightly awkward name. So you're a slice of Vulkan queue family properties. Like so. Probably means we also want to delete that. Just checking. Am I getting use after freeze if I do that defer delete? Or is it going to be done by copy? Okay, let's think about that in a second. We're going to go defer delete queue families properties. Just so we don't forget about it, we tidy up our memory afterwards. These things are so small, it's probably not that big of a deal, but it doesn't hurt. We can then call vk get physical device queue family properties for our physical device. Reference to our count and our raw data to that slice that we've just allocated. Like so. And that loads up a list of queue family properties. What does this actually tell us then? If queue family properties is null, then the number of them is that. Queue families available or queried. Queue family property count. Queue family properties. So this is what it's going to give us out. So we have the queue family property structure is defined as queue flags, queue count, timestamp valid bits, and min image transfer granularity, where Q flags is a bit mask of VK Q flag bits indicating capabilities of the queues in this queue family. Q count is the unsigned integer count of queues in this queue family. Each queue family must support at least one queue. Q count is the unsigned integer count of queues in the queue family. Okay, so yeah, that makes sense. And they must have at least one, so you can't have an empty queue family. Timestamp valid bits is the unsigned integer count of meaningful bits in timestamps. Okay. So I don't think we're going to be needing that. Min image transfer granularity is the minimum. My goodness. Is the minimum granularity supported for image transfer operations on the queues in this? So again, I don't know. I think we might just care about queue flags for what we're doing. I think we might just take the first queue that supports all the things that we're going to need. So we've got those. Can we say down here now? So for queue family properties in queue families properties. That's why the pluralizing is annoying. So these are the properties for a queue family. And what we would like to say, this is going to use... So Odin has this thing for bit sets, which are, I think, objectively nice and neat, and I always forget how they work. So you can see it here. So what's it got? It's got an enum that it's saying I can represent as a bit set, and then it has really nice kind of arithmetic operations on them, or arithmetic-ish operations. Set operations are probably a more useful way of saying it. So what do I want to say? I want to say that the set that I've got from the queue family properties contains... what is a strict superset? These are often used to denote flags. It's much easier than defining integer constants. If a bit set requires a specific size. Okay, we can work this out. So what we could do is we could just write out a whole bunch of ifs. Maybe we do that first, just to sanity check this does do what I think it does, and then we can come back and we look at the bit sets thing. So for queue family properties in this, present supported would be equal to... Is there just an in? Yeah, there is an in. So present supported is equal to... what is the actual thing that it was? It was queue flag dot... is there not one for present? There's graphics. See, because everything that's graphics can do present. So yeah, I think we want graphics and transfer. Optical flow NV, video decode, video encode. So yeah, we're not using those. Is that the full list? Yeah. Okay, so let's go ahead and say graphics supported and transfer supported. I'm not even sure we're going to use transfer initially, but I mean, we might. So I'll be shocked if we can't find a queue family that does both. So if we do this, and we say that is queue family properties dot... Nope. In queue family singular properties dot queue flags, and this one is in queue family properties dot queue flags. So if we get both of those, actually I'm kind of curious how this comes out now. So can we do a format print line graphics support? My goodness, I will learn to type eventually. Transfer supported, and let me see here, if both supported would be equal to I think you do a set of VK In fact, you might even be able to just do dot graphics because it can infer the type from the thing you're comparing it to. So if I've got that, I would like to say that it is a subset of B. Okay, so strict subset meaning it's not equal to. Subset relation is a subset or equal. Strict subset is a proper subset. Okay. Of Q family properties dot Q flags. Not happy. Didn't work. Oh, it might just be because of typos. Q flags. Still not happy. Missing type and compound literal. Is it because I've not told you what type this is? So if I do here VK Q flag, Q flags. There we go. That's the syntax. Can I do a dot there actually? Can I do dot like this? Tell it to infer it? No. Okay, so you have to tell it what type the set is going to be. I think that should give us the right behavior though. So let's come up here, format print line. I hope there's not so many of these that it's going to just spit an amount out that we can't just read, but let's see. And let's close that window. It gives us true, true, and true. False, true is false. False, false is false. Sweet. So that's Odin bit sets. And I think they're right. That is neater than, you know, using numbers and having to shift things around. So I don't need that one. If both supported is this. So I'm going to keep that both supported because I'm going to forget that syntax most likely. So for the Q family, both supported is equal to this. If renderer dot Q is still nil and both supported. So we've not found one yet, and we found a Q family that works for us. Then we are going to save renderer.q is equal to Q? No, because how do you refer to these things? Get physical device Q family properties. Is it literally just by index? Q family properties. That's ringing a bell now I've said it out loud. Q count timestamp valid. I think you might do this by index. So if I come in here and I do like this. No, it isn't that because it's not a Q. Bugger. Q flag bits. Graphics bit, compute bit, transfer bit. So that's what we were just looking at. Q flags is a bit mask. Q family properties 2, and then we're into all the extension craziness. Okay. Bunch of other stuff. Q family checkpoint properties. Q family checkpoint properties. So what actually is a queue? Did I ever have a handle that was a queue? I assume index will be a number. So if instead of this, if I say format print line, both supported, expecting that to be true, and index. Did I not actually do my right? There we go. So it's the 0th one, the first one it found. Instead of if both supported, what do I get if I say Q family properties? We get Q flags, graphics compute transfer, Q count is 1, and the other details. Okay. So what is a queue? We come back into here, it was a handle, wasn't it? So at what point in here do I have a queue handle? I've got get physical device queue family properties. Get physical device queue family properties. Performance query counters. VK performance counter. Wow. There's a lot of detail. A lot more than what we need at the minute, though. I just need to know what a queue is. I'm guessing somewhere in here there's a way to say, hey, I've got this queue family index and I would like the queue. No. Okay, let's save the queue index for now then. Like I said, I have a vague memory that that is actually what we want. And not a VKQ. So let's make you U32. Only because I think everything else has wanted a U32. Oh, we can't make it a U32 because how are we going to represent the bad case? In which case that also doesn't work. Piss. So what I was thinking there is I could make that into a int and have like -1 used for a sentinel value to show that it's not been found yet. But obviously it initializes to 0, and 0 is a legitimate value it can take, so that doesn't work for us. So I could set the sentinel value up here just before we start doing this check, but if we're going to do that, then I think what we might as well do is make a found bool, which I'll write is false just for sanity's sake. I'm pretty sure it will, what's the word? I'm pretty sure its nil value is false, so it'll be false anyway, but I'm not going to worry too much. I think explicitness is good. This will then have an index. No, we're not doing it that way. We're instead going to say if, maybe in fact we can just do if both supported and we'll break. I'll try and avoid a break just because I think they can end up being pretty unreadable, but this is quite self-contained, so maybe that is fine. So you can see it hits the first one and it steps out, it gets 0. So if both are supported, we're going to go ahead and say renderer.q index is not equal to 0. It is equal to index, which it will complain about because index is of type int. So let's just cast it to a U32. Run it. No error. Okay, so we have successfully detected our physical device, selected the discrete GPU if it's there, integrated GPU if not. I guess maybe it is worth something in here to just say blow up if it's still nil when we're finished. So we go through all the devices, and if at the end of this, if renderer.physical device is still nil, panic, failed, pick a physical device. Similarly down here, we say for each of these things, do the thing. Okay, maybe instead of a break, we do want a found. So let's have a found is a bool. Found. I don't have to say bool false, do I? You can just say false. Found is false. If we get to here, found is true. And if we get to the end of the for loop, if not found, sorry, if not found, panic. Sorry, I'm getting texts and it's very distracting. Sorry, what was I saying? Set found to false, go through the list. If both supported, found is true, we break, which is still worth doing because it makes our thing simple, or makes our condition simple. And I guess it's slightly more performant. To say it's performant is kind of silly just because the list is so short that, like, why would we care? But if not found, panic, failed to pick a device queue. I'm going to include index because I don't know if there's something else we do in a minute to actually pick out a queue. This is bothering me now. If not found, so found is false, and this, we do that. There we go. Let's run this and check it doesn't panic. Doesn't panic. Cool, so we picked our device queue. I'm going to also add in there that it's for an index. So I'm not entirely sure. I'm not entirely sure we're done with that, but we'll see. So once we're there, we're going to make a logical device. And I can't remember this being particularly difficult. So maybe we aim to get to the end of the logical device and then we will call it a night. So devices represent logical connections to to physical devices. Each device exposes a number of queue families. How to enumerate them, we've already gone back to. Then there's all this stuff about device groups that I don't think we care about because this is more... I imagine actually if you were running some sort of like AI service and you had this intense farm of GPUs that you're doing to do really big calculations, or maybe you're running some sort of like supercomputer at university to do really like intense like simulation type calculations, then that would be the use case for this. But for our little game running on normal people's computers, I think it's a non-issue. So let's skim past all the device group stuff because I think literally none of it matters to us. Device creation. The things are represented by VK device handles. So we're going to come up here, we're going to make ourselves a device which is going to be of type VK device, and we need to call create device. Now looking at this, it follows the kind of standard pattern. So this, ugly as it may be, the Vulkan API is very formulaic. So eventually, hopefully, this gets kind of burned into your brain. So create device. It needs to take in a bunch of stuff to tell it, like, you know, the arguments it needs to do the work it's going to do. In this case, it just needs the physical device, which makes sense because we're creating an interface to the physical device. Then we're going to have to pass it in a device create info, or a pointer to a device create info, where we'll specify all the details about what we want to create. We have this allocator pointer that I've never done anything with. I think this is where, again, if you're writing your increasingly sort of performance aware game and you're streaming assets, and you know you need very fine control over how the memory is being allocated, then this is where you would do all of that. But for everything I've done so far, it's been simple enough. We pass nil, we get default behaviors. And a pointer to VK device is where it's going to return the device. Now, I think in the first stream I was saying the reason to use Odin is that I like that we can use multiple return values. And this might be an example of where, is it worth the effort? So what we could do with this, we could wrap this into a function called create device, which will return the device and an OK. So we can avoid this in out. Again, I think maybe we do so little of this. Maybe we just write the thing. Let's just write the thing, see it work, and maybe we tidy up after. But example of where Odin is that little bit nice and see, I guess. So let's make a physical device. What do we actually want to do? We're going to want to do a res is equal to vk create device. This is going to take a renderer physical device. Why are you mad? Because you don't take create info. You're going to also want to take in a Pointer to our create info. Let's stick to our consistent casing. We're not going to pass an allocator, and we are going to need device. So in fact, I think we can do ampersand renderer device and just write it directly onto our struct. Clearly, we need to define create info. Create info will be a vk create, no, sorry, it'll be device create info, which I'm assuming it's going to specify for us in a second, but let's just read in case there's anything useful here. So physical device must be one of the device handles returned from a call to enumerate physical devices, which we have done. P create info is a struct containing information about how to create the device. We're going to get onto control host memory allocation. So that may be the first reference we've seen to host. If I remember right, whenever the Vulkan API is talking about device, it's talking about the GPU, or I guess whatever device it is that's running Vulkan through the Vulkan driver, typically a GPU. And the host machine will typically mean your CPU that you're kind of running your normal program on. So we have this annoying kind of like, everything's a distributed system, right? It's like you have two computers running, and the two need to talk back and forth between each other. So the host, it means CPU side. But again, we don't have to worry about that. And we have a pointer handle to where we're going to create our device. VK create device verifies that extensions and features requested in the enabled extension names and enabled features members of the create info are supported by the implementation. If any requested extension is not supported, it must return error extension not present. If any requested feature is not supported, sorry, 10 PM, it's getting past my bedtime, but I'm quite keen to see this bit done. I wish that was a joke. We've got a small child, so 10 PM is pushing it for our house, but hey ho, these are grown-up hours. Where am I looking? If any requested feature is not supported, it returns an error feature not present. Support for extensions can be checked before creating a device by querying this other thing. Support for features can similarly be checked by querying this other thing. So we could do all that checking ahead of time, or we can just have it flame out when it creates the device. I think that works for us. After verifying and enabling extensions, the device creates and returns the application. Multiple logical devices can be created from the same physical device. Logical device creation may fail due to lack of device-specific resources. If that occurs, it gets this other thing. Okay. So we can live with all of that. Let's see what's on device create info. It has the classic S-type, which is annoying. Can I remember how these all look? Be like device create info, like this. Pnex we're not going to set because we're not going to use an extension. Device create flags we might need. Flags is reserved for future use. Okay, flags we're not going to need because it is not set to anything. Q create info count we are going to need. So Q create info count, I think we're going to set to 0. Lies. I think we're going to set to 1. We're going to create 1 Q, and we're going to need to have a Q create info. Interesting. So let's make Q create info, which will, sorry, P Q create infos, and we will have a Q create info. So sorry if it's really irritating that you end up with this mix of casing. I personally quite like snake case just because I think it's neat that you can then use NeoVim to jump forward like by so you could do like F underscore to jump to the underscore, and then I can jump around the word easily, but I can also jump like using the normal NeoVim stuff between words. So I find it's like a really nice way to very quickly navigate around in snake case. That doesn't work as nicely in camel case. If Vulkan was the only dependency we were ever going to use, I think I would use camel case just to stay consistent with it, but it's not. And because we're kind of beholden to our dependencies and how they choose to name things for what the functions are going to look like unless we start writing wrappers, I think it's always going to be slightly chaotic. So, apologies. I know it's ugly, but we can live with ugly. So we're going to have to make that. I think we're going to leave that be for now, though, and we'll come back to it. Enabled layer count is deprecated and should not be used. Interesting. So is enabled layer names. But enabled extension count and enabled extension names is used, or is allowed to be used. Okay. I don't know what that's about. So maybe we get away with just that, which means that we're going to need to come up here and we're going to need to do a queue create info, which will be queue create device queue create info, I guess. Is that the type it is? It's a pointer to device queue create info. I assume that comes with its own S type of device queue create info queue count, queue family index, queue priorities, and pnext and flags. Okay, so I'm assuming flags is about the yeah, like present and transfer stuff that we've already checked it's able to do. So let's flit past all of this. Good lord. So I know I've never written any OpenGL. I've never written any serious OpenGL. I've definitely seen people talk about the fact that OpenGL suffers from extension hell, and that getting anything useful done with it requires so many extensions that it's just a nightmare to get your head around. Skimming this, I wonder if Vulkan is heading the same way. Maybe this is common knowledge in game world, but I don't know. I kind of hoped it being the more modern of the two that would be perhaps a little bit more neatly thought out. Well, at least it's all in there. Device use. Following is a high-level list of VK device uses along with references on where to find more information. Creation of queues. See the queues section below. Synchronization constructs we're going to see later. Allocating and freeing. We're going to see. Oh, we may never actually have to get into details of that. Creation and destruction of command buffers we will end up getting into. And graphic state. So actually this might be a useful little point to bookmark, because that is basically a little short list of everything we're going to need to do. I'm an idiot. I hit escape instead of enter. Rename you to device use. Lost device. Device destruction. So I think we are going to come back and call something like that in a bit, but we're not going to worry about that until we set the validation layers up and it starts shouting at us. There we go. Okay. How do queues work? So you have queue family properties, which we have seen, as discussed in physical device enumeration. The get physical device queue family properties command is used to retrieve details about the queue families and queues supported by a device. Each index in the queue family properties array returned by this describes a unique queue family on that physical device. These indices are used when creating queues. Yeah, that's what I remembered. And they correspond directly with the queue family index that is passed into the vk create device command via vk create device queue create info structure as described in queue creation section below. The grouping of queue families within a physical device is implementation dependent. Okay. Once an application has identified a physical device with the queues it desires to use, it will create those queues in conjunction with a logical device described in the following section. Creating a logical device also creates the queues associated with that device. The queues to create are described by a set of VK device queue create info. We're creating one, which makes life simple. Queues cannot be independently destroyed or instead destroyed with the VK device that they were created from, which is again a relatively common thing you'll see. So like later on we'll get to things like command pools, is it command buffers, descriptor pools. Like, it's some classes of object you instead create, I guess, like a container thing that manages their life cycle, whereas other classes of objects, like I guess buffers, when we get around to making a vertex buffer and an index buffer, just exist independently, and so you have to create and destroy them when you want them. So, at long last, VK device queue create info. We have our S type. We don't need pnext, I hope. Flags. It's a bit mask indicating behavior of the queues, which we probably can come in here and do. So queue create info. Flags is equal to. In fact, will you tell me what your type is? You won't. Probably a VK dot device queue create flags. Oh, what's protected mean? Device queue create flags. A device queue create flag is protected. That isn't what I was expecting. So type U32. Yeah. Okay. I am surprised. We will do some more reading. But queue family index, we are happy to see because we have that on our renderer. So renderer dot queue index. Maybe that's a good excuse for us to say it's actually a queue family index. It could correspond to multiple queues. Queue count is an unsigned integer specifying the number of queues to create in the queue family index, and with the behavior specified by flags, queue priorities. So let's just say in here queue count is equal to something, and the pointer to queue priorities is equal to something else. The pointer to an array of queue count normalized floating point values specifying priorities of work that will be submitted to each queue. Didn't say they're floating point numbers, normalized floating point numbers. So can I literally make priorities equal to a slice of they are floating point numbers. Can I do this and just get it off my back? And then queue count is an unsigned integer specifying the number of queues to create in the queue family indicated by this. So let's just make one. So we're going to ask it to make us a queue, and we're going to set the priority to 1. I'm assuming it says normalized, they mean between either 0 and 1 or -1 and 1. Yeah, there we go. Each element of queue priorities must be between 0 and 1. Queue count must be less than or equal to the queue count member of the queue family property structure. So we could store, or we could look up again and find what the maximum value is. But we know it's got to be at least 1. So we're going to make it 1, and we'll move on with our lives. What is this protected bit about? Specifying usage behavior. Specifies that a device queue is a protected capable queue. Well, that didn't say very much, did it? VK device queue create flags is a bit mask type for setting a mask of 0 or more of these flags. They can be created with a system-wide priority by adding a global priority queue in global priority create info, which we're going to skim over. What is that protected business about, though? It's just not going to tell us, is it? Sorry, I'm trying to not do that clicking. I realised listening back to that first stream, I didn't realise before that I sort of click when I'm thinking. Which is really odd behaviour when you stop and listen to someone else talk. So what actually is this? Specifies the device queue is a protected capable queue. So we come in here, can we say Vulkan protected capable queue? Normally if you create both protected capable and non-protected capable queues with the same family, they are treated as separate lists of queues. Or do we trust the AI overview? Protected capable queue in Vulkan allows for operations on protected memory, offering enhanced security for sensitive data. These queues can read both protected and unprotected memory, can only write to protected memory. To get a protected capable queue, one must create a VK device with this flag and then retrieve the queue using the get device queue2. The concept of protected memory isolating can only be accessed by protected queues. I think we don't need this. Yeah, so it looks like you have to go out of your way to make a protected command buffer. Performance considerations and timing measurements may be less accurate or disabled on protected queues to prevent side channel attacks. Interesting. And some implementations might behave differently when creating both protected and unprotected queues from the same family. Oh, sorry. Okay, which is all to say, I think we can just set no flags. Will you compile? You will compile. At that point, we have a logical device. Is it useful to say in here then, so if we get to the end of that, we say if renderer.device, no, we've got the res, don't we? So we have to say if res is not equal to success, then panic failed to create, let's call it logical device. I don't actually know if we're going to need the queue index past this point, so it might be we can actually just bundle those two together and take it out of our renderer state, but worry about that when we get to it. My god, that felt like a lot of work. Okay, so that gets us to the point that we have ourselves a physical device, we have ourselves a logical device. Okay, so to get our actual queue, we're also going to need... No, we're not done, are we? So, this is all guff about that global priority stuff. We're not worrying about the global priority stuff because I don't think we need it. But we are going to need a handle to our queue object. And this is what I remember. I think you need to have access to a queue because later on when we are creating our commands to kind of dispatch our graphics pipeline calls, I think we have to dispatch them to a particular queue. So it makes sense we need a handle. So let's say all the way back up here where we have our queue family index, let's say we also have our single VK queue. Queue family index, queue index, the index within this queue family of the queue to retrieve. Pointer to queue is a pointer to VK queue object that will be filled with the handle for the requested queue. Okay. So let's come in here and we'll retrieve our queue handle. Oh my god. Retrieve queue handle. and we're going to just call vk get device queue. We're going to pass in our renderer device. We're going to pass in our renderer queue queue family index. We're going to get 0, so we're just going to grab the first one off of there, I guess. And we're going to stick this in queue. So, get device queue must only be used to get queues that were created with the flags parameter set to 0 to get queues that were created with the non... Okay, that's what the AI told us. I would like to think that AI completions and AI questions should be really accurate on the Vulkan spec, because it has a whole heap of Vulkan spec docs to refer to, but maybe that's wishful thinking. Here's a load of stuff where it's telling all about... So here's a load of detail that I'm hoping we don't need to worry about. Queue submission. When you submit to a queue... Yeah, so this is how we're going to actually like submit work to a queue to be done. We're going to need that queue handle. We only have the one queue that handles all of our things, which makes things really easy. I don't know. So one thing that we may end up doing, because I think it does make sense, is the Vulkan guide had you set up to have multiple frames in flight. I think it's the wording people use. So you have 2 frames that you're able to be rendering at the same time, and it means that the CPU can kind of run a frame ahead. So whilst frame N is being rendered, the CPU can be working out the state for the next frame, submit frame N+1 to be rendered, and then wait for frame N to finish before it picks up and starts on N+2. I'm hoping we just dispatch all that work through the same queue, but I don't know that for sure. So we may end up having to come back and make another queue, but that's a problem for future us, because we're now at a point where we've got a queue. So that's pretty cool. So that's our first little chunk of Vulkan code written. We are grabbing a physical device. We're using that physical device to create a logical device to act as our kind of interface for the API calls. We've queried for our queue family index that supports graphics and transfer operations, because I think that's everything we're going to need. Transfer may even be overkill, but I think most modern devices will have a queue that supports both. I have a vague feeling that I may have even seen somewhere that they expect to have one queue that can do everything. So in the worst case scenario, you can always rely on finding a queue that can do all of the operations. But again, I don't know why I think I know that. So big pinch of salt. But we're going to find our one queue, and we create the queue. So we now have our handle. We're not destroying anything yet. So I think probably the next step in our little adventure will be to hook up the validation layers. Once we have the validation layers in, I will add a call to start destroying these objects. And one thing the validation layers will help us keep straight is that everything that gets created and depends on something else will get destroyed. So if I add something to destroy my physical device... Do you destroy a physical device? If I add something to destroy the logical device, everything else will depend on the logical device, and so it'll help us keep that really tidy. Probably not necessary for our program in particular, just because we expect our renderer to, again, like with our window, it'll live for the lifetime of the program. But imagining ahead, we might end up in a situation where we want to have options in a menu that let you change, even up to, like, we might enumerate your physical devices and then give you an option to change which GPU we're using, and it'd be kind of cool to have that set up sufficiently neatly that we could just switch it out. Yeah, that's thinking a long way ahead. The other thing I'm thinking is, I've still got it in my head, it'd be nice to try and set up screenshot testing. again, we're a long ways off of it, but I just think it would help make me less worried about refactoring things and tidying things and moving things around if once we've got it working to where we can render our sprites, if I could just make a screenshot test that said, okay, now let's go through and have it draw each of the sprites that we require, and then we can have a little test suite that makes that all work. Being able to just like throw up and tear down a renderer really cleanly, I think will make that simpler. Because you know, if you imagine you do 100 of those, if they all leave a load of memory hanging around in the GPU, it's possible that those and each of these things that as it starts up loads a load of texture data in as well to remember. So we keep creating more memory on the GPU. Our process is a long-running process that we don't ever like come back to and kill. It's possible we might end up causing actual trouble where we just pile too much image data into the GPU. It's unlikely, if we're frank. What we're building is so simple, but you never know. So we're gonna do that to keep it tidy. It's a good way to see the validation layers, see them working. They catch other kinds of issues too that we'll be thankful for down the line.